Hello, everyone. My name is Ankit, and today I'm joining this conference along with my senior colleague, Dr. Nis Martinson. We both are from Energy Nautics, and it is a pleasure for us to be a part of this conference. The work that I will be presenting today is a renewable energy grid integration study that we carried out for an islanded system using ETAP User-Defined Dynamic Models. Before I go deeper into the study, I wanted to introduce you to our company. So we are Energy Nautics, and we are based in Germany, Darmstadt in Germany. We are a power systems and renewable energy-based consulting firm with a broad service portfolio. So we conduct grid integration studies for different parts of the world, focusing on design, simulation, modeling, and analysis of power systems. We have also been involved in smart grid projects such as for smart metering, smart charging, and remote monitoring of renewables. We are also quite familiar with grid codes around the world, having reviewed and drafted some of them. And we, through our workshops and capacity building projects, we regularly contribute towards the discussion of renewables in power system. So it was one such grid integration study that we carried out for our client that I'm going to describe today. So in the first half, I'll walk you through the objective of the study and give you a description of the system. Then we look into the methodology in terms of the approach for the study, shortlisting the cases, the development of the power system, and the future renewable expansion plans. And finally, we move our focus to ETAP, talking about the user-defined dynamic models, the organization of the study, and then ending with results and conclusion. The study was commissioned in 2019, and the idea was to assess the system stability for the upcoming renewable expansion. So the study was commissioned in 2019. However, due to certain delays, we only picked it up again in 2021. So we still treated 2020 as the base case for the study. As for the national policy, the target was to have 5% renewables as a part of the annual electricity mix in 2023 and 30% renewables by 2030. So these two cases, therefore, served as the intermediate and the final cases for the study. The system is spread over an area of 200 square kilometers with a length of 30 kilometers. The total installed capacity is 480 megawatts, most of which came via the fuel-based generation sources. The total demand was in summer was 250 megawatts. The transmission system of the voltage was system voltage was 132 kilovolts, and there are around 20 or so substations at 33 kilovolt. We did not consider any distribution system in the study, so all the load and the renewables was therefore lumped up at the substations in the system. The project progressed in various stages. So in the first step, we collected data about the system to understand the system. So we looked at the energy resources present in the system, the existing single line diagram, the expansion plans, and the cost of generation, the different generation sources, and the merit order. We also collected information about the dynamic parameters for the generating units as well as their control systems. Once we had that information and along with the possible system development pathways, we did a capacity optimization in Homer to get an idea of the installed capacity of renewables needed to meet the penetration targets. The tool also generates an hourly dispatch profile for different for the whole year, which we then used for shortlisting the cases. So in our case, we for the 3 years, we selected the peak load case and the light load case more during the evening and night time, and the high photovoltaic case during the midday time. For 2030, we had two possible pathways, depending upon if the if the system saw a large share of utility PV installation or a large share of smaller scale residential and commercial installation. So this was done because for the large scale installation, the connection rules are more stricter, and which therefore has an impact on the system stability. So the system in 2023, so for the selected snapshots, it saw around 30% penetration for the high PV case, and for the for 2030 for the PV cases, the system saw roughly 75% penetration. So this was a limit that we ensured because the installation of the PV was more than the total load for the given snapshots. And since there were no grid forming models, we had to keep certain amount of synchronous generators operational in the system. So once the cases were identified, we moved over to ETAP. So we updated the existing single line diagram with the future grid expansion plans. We incorporated the cases in the dynamic models, and we also set up the selected cases. Then we did the stability analysis. So to do that, we ensured that the generation dispatch was as per the merit order, but while also ensuring the enough reserves for the system, and making sure that no voltage violations were observed for any of the buses. In the steady state simulations, we also looked at the control behavior for the different dynamic models to make sure that the responses were as expected before we did the contingency analysis. So the system case matrix looked something like this. So for the year 20, so we had three different years, and for each of these years, we looked at the peak load case, the high PV case, and the light load case. For 2030, depending upon the system development pathway, we had a high floating PV scenario and a high distributed PV scenario. So for each of these cases, we did several contingencies to bring forth different system operational conditions and to check the unit responses, generating unit responses for all possible cases. So we looked at angular stability, we looked at frequency stability, and we looked at voltage stability. The identification of the critical lines and buses for these cases, for these contingencies, was based on a previous study done for the system, which we used. So in general, we ended up with 4 grid states here, and there were around 60 or so study cases that we analyzed. So the power system was majorly a fuel-based system in 2020. And there was hardly any renewables in picture in 2020. In 2023, some of the rental generation fleet was decommissioned, and newer synchronous generators were more efficient synchronous generators were installed. So the generation capacity sees some change here. 2023 also sees installation of commercial and utility PV along with a battery system. So these were the locations of the different commercial PV installations and the battery and the utility plant. In 2030, depending upon the pathway, we see either a high proportion of smaller scale installations, so high residential PV and high commercial PV, while in the other pathway, we see a high proportion of the utility PV installation. So you see the utility PV dominates for the 2030 floating case, while the distributed and commercial PVs dominate for the distributed case. So different dynamic models were used to bring forth the dynamic responses of the different generating units. So for synchronous generator, depending upon the type of the generator, we had either a gas-based governor or a diesel-based governor model. The excitation system model was chosen in consultation with the transmission system operator, again, depending upon the excitation system type. For the residential PV, we used the small scale we use the VEC model for small scale PVs. So we use the PV-D1 model. This is a rather simplified model, and it does not have voltage support functionality during faults, and it only has frequency regulation, the downward frequency regulation. We used it in a static generator element. So we modeled the residential PV and also the other renewable installations via the static generator element. For the commercial and utility PVs, we used the VEC second generation model in combination with a plant controller model. So the idea of using the plant controller was to have the frequency regulation feature also available for these models. We used a lumped load element to link the plant controller model. The battery modeling was also done in a similar way. The model used was BESS model. It's also quite similar to the VEC second generation model, except that it has a state of the charge feature, which is missing for the VEC second type 4AB models. And we linked it along with the plant controller model. I'll now move over to ETAP, show you how the different models looked like and how they were represented. So this is a commercial PV plant. We see the plant controller stored in is linked in the lump load element, while the VEC model is linked in the static generator element. So we see different dynamic models here. The dynamic models are activated depending upon the revision in place. So for the 2030 floating case, this is the model which is active. I will now go inside the model to give you a brief overview of the model itself. So this is the VEC model. We have the reference generation, then we have the electrical control block, then we have the generation and the converter block before we send in the final references to the end element. The references are generated from the plant controller model, which is in the lumped load element, and that's why you see the switches to the link to the references from the plant controller. See, we use the multi-dimensional structure, database structure consisting of the revisions, configurations, loading generation categories to organize the whole study. So we use the idea was to use the revisions to store the different grid expansions, the loading generation categories for the different cases, the study cases for the different contingencies in play, and the configurations for the breaker status and the reactive power operation modes. However, we couldn't maintain such a structure because of the battery element. So for the battery element, we had the idea was to have it discharging during the peak load case, charging during the high PV case, and then only use it for reserve during the light load case. So it meant that the model had to have 3 different reference set points depending upon the cases, which meant that we had to use 3 different dynamic models because reference set points are not linked to the load flow in ETAP, and it can only be done by making by having different models for the same element. So that's why for each of the years, we further ended up with different revisions to have the right battery model selected for the case. So for this study, we majorly used user-defined dynamic models, and I wanted to talk as to why we did so. The built-in models are in ETAP. They are first generation models, so they lack a lot of the new features which the second generation models have. The control behavior of the built-in models cannot be altered, and we wanted to make certain changes in the control behavior of the models. The UDM models also allow for easy debuggability because it's easy to plot the internal control signals and see what's really happening. The UDM models can also be linked to the plant controller element, to the plant controller model. With the UDM models, it's also possible to have reference set point changes during the simulation, which makes it possible to also analyze newer cases. So I'll now move over to the results section. So before we did the analysis for the future years, we looked at the base case to see how the different system responses looked like. So the case described here is the peak load case in the year 2020, where the total generation was 245 megawatts and hardly any renewables. The event simulated here is the loss of the largest generating unit, and this is the mechanical power of different generating units. So we see that the frequency drops to an RDR of about 58.5 hertz before recovering. and settling at around 59.5 hertz. This was because there was no secondary reserve in place, so that's why the frequency didn't reach the nominal value. The frequency recovery was mostly because of the primary frequency response of the synchronous generating units. In general, there was no stability issue seen. No protection limits were triggered, and there were no frequency or voltage violations for the cases in 2020. The next case is from the year 2023. So this is the high photovoltaic case, and there's about 30% renewable generation, and the battery is charging in this case. The event simulated here is the fault in a transmission line and subsequent removal of the line. We see that during the fault, the synchronous generators kick in and push in more reactive power into the system, which is expected from these units. The system frequency sees some oscillations, but nothing beyond the protection thresholds. And in general, there was also no angular instability seen for these cases. What is, however, more interesting for this case is the behavior of the different converter-based units. So here we see the responses for the utility PV and the battery plant, and here we see it for the commercial PVs. So for active power, we see that the active power drops because it is limited by the voltage in the system. However, after the event is cleared, the active power responds as per the frequency regulation and group values to balance the frequency deviations. For the reactive power, since the system operated in the reactive power priority mode, we see that the reactive power either increases or remains the same due to the higher reactive current injection despite the drop in voltage. So we see that these units are contributing towards fault support as well as and later on for frequency regulation. Again, for this case, the system reached a stable state. There were no frequency or voltage violations, and the converter units supported the system during the event. The final case is the case from 2030. It is the distributed scenario. In this case, we had around 75% of the renewables generating. The system, the renewable penetration for the specific snapshot was around 75%. We had to derate the renewables to ensure that enough synchronous generation generators were online for this case. The event simulated here is the loss of the utility PV plant. So we see that the synchronous generators, whichever were active, push in more active power in the system. However, the more interesting response is from the converter-based units. So the converter-based units, because the PVs were derated, they also now push in more active power, inject more active power into the system to bring the frequency back to prevent the decline of the frequency. And this is what we also see from the battery plant. So you see a reduction in the power consumed by the battery plant. We see a faster fault recovery because a lot of the converter units were supporting. And again, the system reached a stable state, and there were no protection limits were triggered. So in general, we had a very good experience with ETAP, and we wanted to talk about what features we found nice and what can be improved. So ETAP, we definitely benefited from the large amount of UDM models that are available right now, and we were mostly able to have the right model for the different units. We also made use of the multi-dimensional database structure consisting of the revisions, configurations, loading categories, and it was easy to organize such an extensive study. The macro wizards also made it possible to reload and batch run simulations, thus saving a lot of our time. We also used the SQLite database export feature to export the results and then plot it via Python. So we were able to automate the whole process. We faced some issue with the model initialization, especially for renewables. In the case when we had to derate them, this was because they did not start more or less from their reference set point, and which led to some convergence issues. We, however, were able to sort it out with some workarounds. The other problem was that because the load flow is not linked to the models itself, it increases the overall number of models in play, which makes it difficult to making it difficult to deal with a large number of models. Uh, so with large number of models, the problem is that if you want to change a parameter or block diagram, you have to open every model and then make the changes, which makes it which leaves little to no room for experimentation. And for our case, we wanted to also try active power priority for the different renewable units. However, it was not possible to do it in the given amount of time and with such large number of models. Then the element out of service is currently a feature which is stored. It's currently a value which is stored in the revision. So if you want to put an element out of service, you have to make a separate revision, which then increases the number of revisions in the system, and makes it a bit more complicated. So I'll split the conclusion in two parts. The first part, we talk about the system more from the systemic stability perspective, and in the other half, we discuss the our experience with ETAP. So our conclusion was that the system was observed to be stable for the given system configurations and the expected renewable penetration. The assumption being that the future converter-based units, they would have the fault write-through and the frequency support functionality. The conclusion was also limited to the tested scenarios. So, I mean, it could probably change for a different renewable penetration, higher renewable penetration, or different dispatch loading, or on different network configuration. Our experience with ETAP. So, as I said earlier, we were able to run everything that we wanted to for the study. So, our experience was quite nice. We benefited a lot from the different dynamic models which are provided in ETAP, both built-in and in UDM version, and for UDMs. We were able to run all the studies, and we also wherever we were stuck, the user support always was there to guide us through and to help us out. So they were also quite thorough, very thorough with their answers, which was also super nice. So in general, our experience with ETAP was quite good, and we were able to achieve the objectives for the study. So that's it from me, and thank you for listening. We will be there to answer any questions that you have.